This is the second part of the permeability lectures. There's only two of them. These are more, the last time we talked about the basic theory behind permeability, and now we're going to look at some applications of that theory. And some of them we're going to cover in more detail than others. Permeability in itself is a very wide-ranging topic that probably deserves its own treatment. And in fact, like I say, if you're getting environmental considerations, it's absolutely essential to understand many of the things that go on with permeability. I'm going to start by noting that there is another chart, more easily legible, for permeability. Permeability, one of the things for highway materials, permeability is an important consideration with pavements because undrained or improperly drained pavements, let's forget about undrained, that's kind of the always and never thing. We have pavements that are drained well, and there are pavements that are drained poorly. Poorly drained pavements have problems, and pavement drainage is in part, and of course, under the pavement you have your aggregates and what materials, and many of those are there to get the water away from under the pavement and to eliminate the problems that occur from that. So it's an important, there's all kinds of little topics that don't really impact us directly in conventional geotech, but where permeability is very important. And then there's the other table, which is probably a little easier to read, with typical values of permeability. And it's always dangerous to use typical values, but in the case of permeability, frequently it's maybe the only thing we have to go on. So, all right, how do we find it? We've talked about doing laboratory tests, and I told you right up front that permeability is the hardest quantity in soil mechanics to properly quantify. And so, because in the lab, because of the issue of getting a disturbed sample, a truly undisturbed sample, from the field to the lab. And if you disturb the grain structure, you screw up your measurements of permeability. And some damage is almost inevitable. So we try to do it from field. One of them is empirical correlations. Based on tests bolstered by a varying amount of theory and also a varying amount of testing. The most common is Hazen's correlation. It goes back to the early part of the 20th century. Hazen was a water official in Massachusetts who came up with it. And basically, the correlation is very simple. It is K is equal to C times the D10 squared. We've talked about the D10 before, and we actually saw it in action with, we've actually saw it with capillary rise. So therefore, and the K is in centimeters per second, which is, I told you that it comes in many units. It's probably the most common units. And then C is 0.8, C 1.2. Now, let's talk about empirical correlations in geotechnics, because this is their first lesson in how to use them. Many empirical correlations in geotech, and this drives me crazy, especially if you're someone who deals in two sets of units. Or three actually with MKS and SI, or four if you throw in CGS. And actually, K in this case is a CGS quantity. So, what's the deal here? Well, this is a purely empirical correlation. there's no units. You know, I know that D10 is technically in millimeters, but that doesn't have anything to do with anything really. You just do this. If you wanted to readjust the C coefficient to do another unit, you can do that. Generally speaking, C is anywhere from 0.8 to 1.2. For our purposes, we usually use the unity. And, you know, C, but this is a purely empirical. The units don't, you know, unit analysis here doesn't apply. And some of my students try to get real fancy with it. Don't. Now, there are some empirical correlations that are, and others which are like this. And we're going to touch on them as we go along. There are some where we try to fix that problem. The biggest problem we run into is the fix that we see most often is empirical correlations that talk about stress or pressure. They'll normalize them using the atmospheric pressure. And we actually saw that in action with the SPT correction, the N160 correction, C sub n. With the SPT correlation, we have two formulas. The formula that I presented to you, although it's kind of buried in there, is corrected by atmospheric pressure. The other one, not to the same extent. You cannot use it directly in SI units, or it doesn't have two forms, one in SI and one in US units. So that's a problem you're going to run across with many of these empirical correlations, and you're just going to be careful about them. Things are getting better, more as we see, you know, double unit situations. You're seeing more books and whatnot reformulate them for either have two different versions of them, or something, or you know, non-dimensionalize them more generally. But a lot of them don't, and this is probably one of the most important examples of that. So these are typical values. They're limited to soils with a D10 in a certain range, and CU is less than 5. You need to look at that range. Another thing about empirical correlations is most of them were developed for a range of values, of parameters, and should not be used outside them unless you're just forced to. So you look at the chart and you see there's other correlations. There's Hazen's is there, and Burmister's is there, and the lab test values are there. And all of these can be used. In fact, you could use Hazen's correlation from that chart if you wanted to. That's perfectly acceptable. Maybe a little clumsy with a spreadsheet if you're trying to use a lot of it, but you know, in any event, you can. It assumes laminar flow as always with soil permeability. So let's look at an example. Given the soils below, the D10 is 0.15 and D5 is 0.08. Uniformity coefficient is 8 and the void ratio is 0.6. Find the hydraulic conductivity using a variety of methods. And the methods we're going to look at is just two of them, Hazen's and the laboratory test charts. Hazen's correlation, you know, is the easiest one, obviously, but we really can't use it since the uniformity coefficient 8 is greater than 5. So the lab test can be used since both of those. In other words, CU can be from 2 to 12, and 8's in the middle of that. And D10 over D5 is 1.8, which is greater than 1.4. And you know, where I got that from, you'll read this right here. All this is this and this are all taken from the all taken from this chart. And of course, with the laboratory test results, they've also got multiple void ratios as well. So you simply, wait, I got ahead of myself. This little red line shows is actually the solution to that problem, where you come up from here D10 up to here, 0.15, then come over. And you can actually go either way in this case, but what units you want. You can either get it in centimeters per second on this side or feet per minute on this side. You can actually go over this way or go over this way, depending on what units you wanted to use. And that's nice. But we, so basically, and we do both in the example. I either have 0.1015 centimeters per second or 0.05 feet per minute. And you're done. Field permeability tests and dewatering wells. This is a complicated subject, and I'm not going to spend a great deal of time on it, but we're going to just go through it very quickly. Field permeability tests measure the coefficient of permeability of in place or in situ materials. The area and length factors are offered as shape factor or conductivity coefficient. Even though we don't have the sample disturbance issue, we still have to deal with the fact that permeability is highly sensitive to both the natural and test conditions. Field permeability are also the inverse of the pumping problem. To do that, we need to make a definition of confined and unconfined aquifers. A confined aquifer basically is an aquifer with a relatively impervious. One thing you're going to hear me throw out is impervious and pervious materials. Now, obviously, we know that that's a relative term because all materials are permeable, but not all of them are easily permeable. And so, for example, a horizontal aquifer, connected between impervious strata, you got one above, one below, and you pump it. Basically, you set this well up and you pump it down, and you get a nice little curve that looks like that from it. And that means this area is dry. We'll come back to that in a minute. With a unconfined aquifer, there's no impervious layer up here. It's just pretty much all pervious to the top. But you get a similar type of curve here. And water flows from outside to inside, and then it flows out the well. And sometimes you'll get a situation where you'll get a combination of combined and gravity flow. With a confined aquifer, this is where this is sort of a two-brain situation. On the one hand, if I know the flow, such as I start with this equation. If I know the flow, I can compute the coefficient of permeability using that equation. And little r and big R are two radii. And normally what I do in a test like this is I will set up one. Actually, I could set up two wells and measure the height of this from here and here, for example, and if I know the two radii and the two heights, I can compute it. Usually, particularly if the well is of decent size, the little r is actually just the radius of the well being round, and then we use that for one of our values when we drill one well. So we can compute K that way. If, on the other hand, our job is to dewater the well, so in other words, get the water out of there so we can work in the dry, then we just simply rearrange the equation and go the other way. And that's pretty much the way we can use pumping tests to either estimate conductivity on the one side or use it to determine how much big of a pump we need to keep the thing going. Of course, you say, well, how do you know what pump to use to start with? You make an estimate, you stick a pump up, you turn the thing on, and then you see what happens. Hopefully, if your estimate is good, then the pump size will be fine. You'll be able to still measure the flow, which is smaller than capacity. In other words, your pump capacity won't be too low. An unconfined aquifer is the same kind of thing, only the equations are a little different. But it's the same concept. Sometimes you'll see on big R, in other words, the radius away, they'll try to estimate the, well, in driven piles we call it the magical radius for that kind of thing, or more to the point, it's the radius at which, in theory, this radius never touches the top. In reality, for practical purposes, it does, and we've got ways of estimating or guessing at what that radius is, which means if we can do that, then we can just call that the big radius, and then the little radius on the inside is the welt rail, and we'll live happily ever after. So that's also possible. Dewatering is an important topic, and it's not one that gets a great deal of coverage, because it's really kind of one of those things where if you have a major dewatering issue on a project, you call specialists. Is about the only, and that's one reason why dewatering. In earlier, particularly with the military, they were spending a lot of time on this subject. Not so much now. It's very much of a specialist type of thing, but it's very important. As you see here, this was Lock and Dam 26 back in the 1980s, where they had to dewater a large area to build the Lock and Dam 26. So they used a cellular cofferdam, and they drained. They drove the cellular cofferdam, they drained it, and then they were able to work in the dry. You see them driving piles here in the dry. We are experiencing very much the same thing with, right at the moment, those of us who live in the Chattanooga area with the Chickamauga Lock and Dam. It's very much the same kind of thing. So, but dewatering is an important, because usually working in the dry is really, even though it may seem to be a lot of trouble to put the cellular cofferdam in, you can, it's usually the most straightforward way of building a structure like this. And if you don't believe me, go ahead and do it. One day I mentioned the Olmsted Lock and Dam, which is finally finished. And just Google the cost overruns on that thing, and you'll see what I'm talking about. Another way of doing permeability is a rising head test, or its relative percolation test. These are really work the opposite of a falling head test in the lab. And all you do is you drill a pipe in the soil, you take the water out of it, and you watch how fast it comes back. It's just that test in reverse, and you see the equation for it there. And it's very similar to that. It's a very, it's a lot easier, and you'll see that it's good. It's easy to run if and only if the groundwater table is relatively close to the surface. It's easier to run. Obviously, the deeper the groundwater table is, the harder it is to run the test. But you can learn, if you can do that, it's a lot more accurate, and it's not a very intrusive way of determining the admittedly low coefficient of permeability for a clay or silt. One of the things about permeability is that there are two things. One of them, we talk about layered soils. The resistor model. If we have flow, there are very few stratigraphies that are completely uniform. Very few. Most of them are alternating layers, and they can be alternating. Usually there's some cohesive soils, Particularly with permeability, the differences in permeability between layers can be very significant. So we might want to know how to, determine the overall hydraulic, the coefficient of permeability of a layered soil. Well, how you do that depends on which direction the water flows in relative to the layering. If the layering, say the first one, is if you have horizontal layer, we're going to stick with horizontal layers. You don't get the other very often. Vertical flow has to go this layer, then this layer, then this layer, then this layer, then this layer. It has to go up or down through several layers. And act like a resistance in series, and the equivalent overall vertical permeability looks like that. For horizontal flow, you got the layers are this way, and the flow is this way. So it flows some through this layer, and then some through this layer, and then some through this layer, some through this layer. And the resistances are in parallel. And I'm using an electrical analogy to make it simple. And the equation looks like that. Now, particularly with vertical flow, one of the things you will find is that, particularly with vertical flow, is that the low permeability layers will generally be the major factors in terms of the overall conductivity of a layer, and particularly vertically. But this is a handy way of determining what those might be for a layered soil, and most of them are, as I said. Another thing we deal with is anisotropy. We're not going to do a lot with anisotropy in this course. In many cases, for example, the Varve clay, which is layered like this, obviously you're going to get anisotropy because your horizontal, your vertical, your KV, your KH are obviously not going to be the same with a layered soil. And Varve soils are the layers are very small and packed together. But anisotropy is something, virtually all soils are anisotropic to some degree, just by the fact the deposition was due to gravity. So this is almost, we're not going to spend a lot of time talking about this, but you need to be aware of it in soils. Now we come to two-dimensional flow analysis. Some of you may have been thinking, I can't understand why, we spend so much time on one-dimensional flow analysis, because, what flows in one dimension? And that's a legitimate sentiment. So we're going to fix that problem. What about two-dimensional? Or actually, it's three-dimensional flow analysis. And once again, as was the case with the one-dimensional problem we looked at the last time, we're going to instead of using a true three-dimensional representation, we're going to use a two-dimensional representation per foot or meter of the representation. There are many methods. We could do theoretical equations from complex analysis. Voigt shows some of this, but if you look at Voigt really carefully, you'll realize that really and truly it's not very not very informative. It takes very simple geometries. A more sophisticated application of theoretical would be the Russians developed some methods, and they were popular for a while until but digital computers pretty much put all those out to pasture. Flow nets are traditionally the most common method in use, and it's an ingenious approach to a very complex differential problem. There's the electrohydraulic analogy, which is kind of the equivalent of, we see some of that in stress analysis as well, where we use electric field in a material to simulate flow, and then finite element methods, which are probably today for most real geometries are probably the best way to do it. And we're going to actually see some of that applied in this course. The theory is Laplace's equation. It's an equation in 2 dimensions, I know some of you are looking at that and you're thinking, he's got to be kidding. We're not going to be able to do that. Actually, there are a number of ways of looking at that equation. One of them, of course, is no, we're not going to actually solve that equation directly. But I want to mention a few things about it. First of all, you'll notice that in the x direction and the y direction, I've got 2 different k's, and the k's refer to the anisotropic condition, which I talked about just a minute ago. And that's one thing. So and if you don't worry about anisotropy, K1, K2 are equal, and they can be divided out. Number 2, it can be also applied to electrical and stress problems as well, and is. It can be applied to the one-dimensional case as well by eliminating one of those equations, usually y. Although, in what direction you're in. Or you can rotate the axes too. So there are all kinds of, it's an important equation. You see it a lot in nature and engineering applications. So you might want to, but we're not going to actually directly solve that. I said the best way of solving it is finite element methods. One interesting aspect from a fluid dynamics is that we have a lot of different if you're all remember fluid mechanics, we talked about the Navier-Stokes equations, and then they're not easy to solve. It's done now with computational fluid dynamics and that sort of thing. And then if you take the viscosity out of those equations, you get Euler's equations. And then if you keep simplifying it down, really the simplest form, this assumes it's laminar, irrotational. This is the simplest application of simplest fluid equation you're going to find. And we can use it in soils because if it gets any more complicated than that, usually let's just put it this way. Usually the flow you're dealing with, getting it through the soil is the least of your problems. The most common way we've done it, and a good way of illustrating it, is flow nets. Flow nets go back, I would say, to the maybe 20s and 30s. 1920s, 1930s. We're in the 2020s now. How about that? And basically, they're a way of actually putting, of actually replicate. They do several things for us. One of them is they show us which direction the flow goes in, and give us an idea of how it gets from one place to another. Second of all, it basically reduces a 2-dimensional problem to a series of parallel 1-dimensional problems. Number 3, it's a way of doing Laplace's equation in a very simplistic way, and surprisingly it's worked. But there are 2 things that we need to be good at to actually do flow nets. The first thing is drawing, and both of them actually date back to our time in elementary school. Now, elementary school is a very potentially touchy subject for my own students, because I happen to go to a church with a large contingent of educators, and most of the educators go all the way from kindergarten through graduate education. And they are well entrenched in certain school systems, and if my student is a product of that school system, there is a possibility exists that I can find someone without a lot of trouble that knows the student from when they were in second and third grade. Most students find this freaky. But in any event, there are two things, but now I can appeal, but with that out of the way, I can appeal to people's elementary school education a little bit easier, because there are two things you learn to do in elementary school that will apply in flow nets. One of them is draw. To draw a flow net properly, I'm going to show you that requires a little bit of skill. And one of the things I found is that many of my students are poor at drawing. And I think a lot of that is due to the digital revolution and the fact that we don't really draw much of anything anymore. I've had a few students with the artistic ability to do it, but most of them aren't very good at drawing. With that, I had to make a concession. Many of my colleagues still require you to draw flow nets. I will not. Actually, you can have a computer draw a flow net for you, and it'll do a better job. But if you have it draw it, you have to learn how to interpret, and that leads to the next problem. The other thing you learn to do in elementary school that you're going to do is count. And that's where most of my students trip up. Let me look at this flow nets and I'll see what I'm talking about. We have this flow. These two are identical situations, and this is really the simplest flow net. It's symmetric on both sides. It's the simplest. There are several things that, well, I've got two things. One of them, these are flow channels. This is a flow channel. This is a flow channel. This is a flow channel. And for that matter, that's a flow channel. And so I count the number of flow channels. Basically what I'm doing is I'm taking this nice two-dimensional problem and I'm dividing it up using the flow channels into a series of one-dimensional problems. And you say, well, you're going to compute for each. No, it actually gets better than that. So that's what I'm doing. The second thing I'm going to do is divide this up into head drops. Say, for example, that the difference between this and this is 20 feet. And so what I'm going to do is I'm going to divide this up into equipotential drops. 1, 2, 3, 4, 5, 6, 7, 8. Remember, I told you about counting. And for every time we have every equipotential drop is 20 over 8 feet. This is which it's 2.5, I think. 2.5 feet. So therefore, from here to here is 2.5 foot head drop. From here to here is 2.5 head drop. From here to here is 2.5 head drop. 2.5, 2.5. If you add them up, by the time you start with, if 20 here, it's 0 here. These cancel each other out. 20 down to 0 in 2.5 foot increments, since there are 8 of them. Now, according to the rules of flow, there's two things I'm going to bring in the complete set here of rules, but for the moment, first of all, these have to be for our squares or rectangles. We're going mostly squares. There are two rules. One of them is that these have to be these lines and these lines are perpendicular to each other. In other words, the potential drops in the direction of the flow. This actually shows the direction of the flow, and then this shows the head drop, and these are supposed to be, and by combining those two in a disciplined way, you can get this. That's the tricky part. The second thing is that ideally, the aspect ratio of these are, in other words, that this distance and this distance and this distance across here are basically the same. Now, it's little, you're looking at this and you're thinking, that's not that's, but it's as close as possible. You can have them where the aspect ratio is not unity. It's harder to draw that way, and it complicates the solution a little bit. For our purposes, we're going to try this. Most of the time we try to, unless we're just forced to do something different, we try to avoid aspect ratios other than unity. They're they're much harder to deal with. And there's one other thing. Notice that this has 4 flow channels and 8 equipotential drops. Somebody else came along and decided, well, we'll show you. They did the same thing. There's 5 flow channels, and there's 10 equipotential drops. And you're saying, well, is the flow different? Well, of course not. Of course not. It's not different. How do you take that into account? Well, it's not. It's just you just divide it up more fun. Now you might get a more accurate answer using obviously a finer mesh should give you a more accurate answer. But in this case, it gives you the same answer. Because let's look at the basic equation. The basic equation states that the Q, the flow from one side to the other, is equal to the coefficient of permeability, and we're going to assume that it's, in this case, isotropic, and there's a uniform stratum, times the elevation difference between the upstream and downstream limits. In other words, the difference between that and that, times the number of flow channels in the net over the number of equipotential drops. That's it. The tricky part is counting, and the reason why I put this, which came from, as you see, the U.S. Army Engineer District in Little Rock, shows you count. You have to count. If you screw up the counting of the flow channels, if you screw up the counting of equipotential drops, you're going to get the wrong answer. So this is the other elementary school skill that you need to apply in this case. And that's pretty much flow nets. That's how you analyze a flow net that's already drawn. Now this is from NAFEC DM7, and this shows you the flow net and an example. The little example is right here. And you can count, this is a fairly elaborate flow net. It's got everything you'd want here with a drainage blanket and all this good stuff, but pretty much it's the same as in the simple case. And I would suggest you go through this example because you have the equation's the same, and basically you would simply plug and chug. You have to count. Now you can count these and confirm that it's right, but that's all there is to it. The tricky part, like I said, the tricky part is always has always been counting. Counting has always been the problem with this. And now we do a lot of things too. Obviously, under a dam or something, we usually try to minimize it. One way of doing it is by driving these fancy sheet pylon walls, and we'll talk about that later. But in any event, that's your example. It shows you how it's done. It also shows that you can use them in anisotropic soils by doing some scaling. And you can do that. And like I said, it's not that difficult. It's just that students screw up. The biggest problem I've seen over the years is students screwing up the counting. Next thing we want to talk about are seepage forces in soils. Anytime water moves through a soil, it exerts a force on the soil. and Voigt has a long treatment of the subject. In simple terms, it's equal to the unit weight of the water times the hydraulic gradient. There are seepage forces of many kinds. The most important one is upward flow. In other words, water coming out of the soil moving upward at the ground level. And that you do a soil boiling is something you really want to avoid, particularly in a dewatering operation. One of the problems with soil boiling is that if the flow of the soil is fast enough, really, or has a high enough gradient, and the gradient and the gradient, the rate of the flow, when they're all related, as we all know, then we have a situation called soil boiling, where instead of the soil just staying and the water go through, the soil decides it's going to take a hike and it comes up. Since usually this takes place in pervious soils, sands and whatnot, the situation where you've got a upward flow through a soil which is unable to remain in place and it just kind of bubbles up into a liquid is called quicksand. And it's been the subject of many stupid Hollywood movies where people actually are sucked down to the quicksand, when in fact the flow is moving up, and if the person knew how to swim or at least float, they could survive the quicksand. So that's what you get for believing everything comes out of Hollywood. But let's do a little math. How do we know, how do we know when to worry about this? Let's start with the equation of flow of the hydraulic gradient, which we learned the last time, and it's given in a little bit different form in Voigt. Now we equate the change in pressure to the total stress from the soil weight. In other words, basically, we've got this force going this way, and then we've got this gravity force of the soil this way trying to keep the thing in place, and we equate the two, and the critical hydraulic gradient, the gradient at which soil will start coming up on us, is equal to the minus gamma submerged over gamma water, or 1 minus gamma saturated over gamma water. Traditionally, Europeans have preferred to express that as a negative number. In the U.S., it's normally a positive number. Now, how do we use that? Let's start with the upward flow example we looked at the last time. We compute the hydraulic gradient is 2.333 upward, negative. See, that's why Europeans are more picky about that. There's an upward hydraulic gradient is negative. That means that you got, for upward flow. Assume a soil saturated weight of 20 kilonewtons per cubic meter. You find where soil boiling might take place. The factor of safety against that is equal to, and this is why we compute the I critical, is, obviously the factor of safety is equal to the I critical over the gradient we have. If the gradient is smaller than the I critical, then we're at least have a factor of safety greater than 1. Let's just put it that way. Whether that's acceptable is a different story altogether. If it's below that, it's, definitely not acceptable. So we take the solution. And 20 kilonewtons per cubic meter is not an unreasonable unit weight for a soil. We compute the submerged unit weight is equal to 10.2 kilonewtons. That's 20 minus the unit weight of water. And we go reinforce that to 10.2. Then we compute the critical hydraulic gradient. We're not going to worry about the negative. Is 10.2 over 9.8, which is 1.04. That's typical. That's pretty typical. Usually, if you do a little math, generally speaking, submerged unit weights, in fact, one of the quick and dirty ways we can use to compute the submerged unit, we do this in retaining walls, is say the submerged unit weight is half of the saturated unit weight. because soil weights run in general about double the unit weight, the unit weight of water in round figures. So therefore, if you do a little math, you realize that a critical hydraulic gradient should be plus or around unity. But if we divide that by the hydraulic gradient we have, we get, and if you do both pluses or both minuses, doesn't make any difference, you get 0.45, which means you're in trouble. It also means that problems like that were developed artificially without any consideration for what they really might mean. In terms of, if you actually set a real soil up like the problem we had and ran it, you'd have soil boiling, have serious soil boiling. Some mitigation will take place 2 to 3 meters of water, but you're still going to have soil boiling. Now, another way of computing that is to account for the force is you've got is to actually go, and this is the blow by blow, and you can look at it of basically doing a static analysis on basically a piece of that soil and finding out what your downward forces and upward forces and per unit area, since we're not given the area, and we're still got problems is the result of that. So that's the other way to do it. That shows you, again, this is a static equilibrium problem, like so many we have in geotechnical engineering. An example of a situation like that is sheet pile cutoff. Basically what that involves is taking two walls of sheet piling, driving them in parallel, and then usually digging down into them, and then working at the bottom, or from the bottom up, depending on what we're doing. The tricky part is keeping it dry. Now we're going to talk about, the structural aspects of that in foundations. But for this, in this case, we're going to strictly talk about keeping the thing dry. And that leads us to a couple of things. One of them is, what's sheet piling? Sheet piling is a type of retaining wall that is driven in the ground by driving or pushing, and it's a relatively thin cross-section. Sheet piling was first developed in the late 1800s, and the first major use of that was raising the USS Maine from Havana Harbor. You ask, what is that all about? That's a little bit of American history. Going into the 1890s, Cuba was a part, and Puerto Rico for that matter, were part of the Spanish Empire, and the Philippines were part of the Spanish Empire. And there was a lot of sentiment in the United States to do something about that. And there was a lot of independent sentiment in Cuba at the time as well. So, with the help of cheered on by our then newspapers at the time, it's our media, we got into a war, and one of the things that justified that was the sinking of the Maine. The Maine was a U.S. battleship docked an anchor in Havana Harbor, and it blew up. And it went to the bottom. Now, it probably wasn't accidental, but the U.S. said that the Spanish sabotaged it, and they went into war, and Cuba became independent, and the Philippines were under our rules in 1946 after World War II, and Puerto Rico became part of the United States. And that's why, in fact, we actually invaded Puerto Rico. And so that's why Puerto Ricans are Americans, and Puerto Rico is part of the United States. And I have a little piece that kind of goes into more detail about that. But in any event, just to remind everybody. Now, the problem with this is that the Cubans got their independence, and now they had the problem of, don't look now, but we still got this battleship at the bottom of Havana Harbor. So what do? So what we did was we built a cofferdam. You can see a photo of that right here. And we took that and we drained it. We learned a lot of things like don't use cohesive soils for filling cofferdams, but we got the Maine out. we got it out. The Cubans got their harbor back, and everybody moved on to something else. But in any event, that was one of the first major uses of sheet piling. Not the first one, but one of the first ones. Material sheeting can be cold or hot rolled in steel, and we'll get into more of that with foundations. Aluminum it can be extruded out of aluminum, extruded out of vinyl, pultruded out of fiberglass. It can also be concrete and wood sheeting, which is surprisingly has held on better than I thought it would. There are different types of sections, and we're going to talk about that in foundations too. Z-type sheeting is more common in the U.S., and traditionally that's been true. And U-shaped, which I show you the arch sheeting, which I show up here in the top, is more common in Europe, although we're starting to see a lot more cross-fertilization and stuff roll on both sides of the Atlantic. And it used to be there was a nice clean distribution the way the Americans did things and the Europeans did things, and now it's more mixed up. The flat wall, however, is what you see with this cofferdam at Chickamauga, where you dry them in large cells, round cells, which is what they did, and they drove them in large cells, and then they fill them, and we fill them with gravel to keep for good, nice drainage. We're going to talk about how important that is with retaining walls. And then instead of, in Z sheeting and U sheeting tend to take a load in bending, flat sheeting takes it pulled. So, and then we have arch shape sheeting, which is more common for non-ferrous materials and smaller constructions. Different interlock styles depending a lot on how the sheeting is made, and also where it comes from. Again, Americans have preferred ball and socket, double jaw, that kind of thing is more European. But again, we're seeing more cross-fertilization. So let's look at a flow net and soil boiling example. We have this double wide wall. It's 32 feet across. We're going to split it according to symmetry. Like that, right there. 16 feet on one side and 16 feet on the other, and we're going to assume that they're the same. And so the saturated unit weighs 115 PCF, and the K is 0.0003 feet per second. What kind of pump are we going to need to keep this thing keep our people working in this side of this thing in the dry? Okay, we give some parameters. The depth of excavation is 38 feet. It's 32 wide, so we're going to split it. There's an impervious layer 20 feet below the toe of the sheeting, really like a rock or something like that. The length of the sheet piling is 46 feet, and if you do a little math, you will realize that you can compute that length right there. The water table at the excavation level, the excavation side, you can see that. The water table is at the excavation. In other words, it's right here. The water table is 6 feet below this way, right there. We want to compute the factor of safety against soil boiling. So we draw a flow net. Actually, let the computer draw the flow net for us. What we're going to do, obviously an FE program is going to come up with a solution. We're going to see if the flow net it draws justifies, it can be the solution. And what I do is the water table, the flow net extends from one water table on one side to the water table on the other. And it's got 16 equipotential drops, count them, and 4 flow channels or flow tubes, and count them too. Their aspect ratio is essentially unity. That's one thing you can pay for with a you get an aspect ratio unit. I mean, you should with a computer drawn thing. And the distance between we'll see how important this is between here and here is 4 feet. Flow net equation. I added that B over A as an aspect ratio. You can actually use that. It's easier to compute what an aspect ratio is, to draw the aspect ratio. So we're B over A is unity. All I do is plug and chug into that equation. That's all we do. The HW is 32 feet from here to here. The Q is given, 4 over 4 flow channels, 16 equipotential drops. That's it. The important thing is you have to count properly. And I would strongly suggest you take the slides, which are separate from this lecture, the same, pretty much the same what we got here, and count them. Learn how to count these things. It will save you a lot of grief. Now I want to know if when my people are down there that they won't fall in the quicksand. Now, if they do, it's bad, because what will happen, what that really shows you, you got soil coming up and you're dry, working in the dry isn't working in the dry anymore. Unless you've got a film crew to do a stupid Hollywood movie, you're in trouble. But assuming that that's not happening, we want to find that flow grade. The total head change is 32 feet. That's the total head change. The number of equipotential drops is 16. So 32 over 16 is 2 feet. The length of the drops at the bottom of the excavation is 4 feet. The hydraulic gradient at the bottom of the excavation, in other words, let me back up. This is 4 feet. The head change between this point and this point is 2 feet. So therefore I'm getting ahead of myself, is 4 feet, is 0.5. The critical hydraulic gradient is equal to 115 over 62.4, which is the submersion unit weight, over 62.4 is 0.85, which is on the low side, because it's, 115 is a little looser than usual. And factor of safety is 0.85, 0.5 is 1.7, which is not bad. How bad it is depends a lot on your application and how much confidence you have in that unit weight figure, and how much confidence you have in your analysis. SEEP-W is a package. Actually, the student version is free. It develops a final model that looks like that. Model results. The gradient at the bottom of the excavation is 0.48. In other words, the gradient here is 0.48. The factor of safety that gives 1.77, which is pretty much in line with what we figured. And the total flow is 1.02 gallons per minute per foot of wall. You have to double that because you've got, if you recall, it's two-sided, so you got 1 gallon minute base come from this side and 1 gallon minute come from this side. An additional problem is to compute the effective stress at the bottom of the elephant. I kind of did this just to drive point at home. I did the last time. The upward flow reduces the effective stress. And this is another illustration of that. If I had a hydrostatic case, in other words, the water wasn't moving, the effective stress, water table's at the surface, it's easy to compute. Total stress is 4 feet times 115 is 460. Then U is 4 feet times 62.4 is 249.6. If I had this hydrostatic condition at 210.4. The actual case is shown on the other side. Z is equal to 4 feet. The sigma, the total stress is the same. The U is what is different. And then I would get a much lower effective stress. When that effective stress hits 0, you've got problems. But you see that it does reduce the effective stress. This is a topic I've covered in the past. A couple of topics I've covered in the past more detail, but not so much now. This is one of them. Uplift pressures. As you traverse dam, particularly from one to the other, the water, I told you that the head drops as you go from one side to the other. And basically, that being the case, that means that the water pressure decreases. Well, the thing is, you remember about static water pressure from Pascal's law is that it not only works this way, it also works this way. Here we go, this way. It works in every direction. So the additional pressure is not only pushing it through the soil, it's also pushing the dam up. And if you've got too much of it, the dam's not heavy enough, then the dam will come out of the ground, which has actually happened in the past. So we developed these uplift pressures. And this shows you how that works. Again, I don't normally spend a lot of time on this. Usually the Corps' methods, the Corps of Engineers' methods of doing this basically assume that the hydraulic pressure varies linearly along the bottom of this thing, and they take an average and whatnot, and you've got to force upward. This does it more of the head drop by head drop method, which is where most of the textbooks do it. So with that in mind, that's what we have for the hydraulic. For why hydraulic gradient is important in terms of uplift pressures. Another thing about it is filters. Now, what do we need a filter for in geotechnical engineering? That's what I'm about to explain. A filter if a water flow, we put down things in soil called drainage blankets. And what a drainage blanket is, very simply, is a situation where we've got a very low permeability soil. We want to get water through it. Rather than digging the whole thing up, what we do is we put a layer of gravel, usually gravel. Well, the problem with that is, you just put a layer of gravel and then dump the cohesive soil on top of it, is that the grains in the cohesive soil are much smaller than not only the grains in the gravel, but the voids. And what they will do is the grains will filter into, the gravel, and they will clog it. And we'll get to the point where the gravel is no better than the soil around it, because the water travels through the voids. That's why you put the gravel there to start with. What do? The traditional answer to that are filters, where we start with and sometimes you'll do this, where we would put, say, one or more soils. For example, if you have a gravel, you might want to put a sand filter, and which is basically a covering on either side of the gravel layer, to prevent the little particles from getting into the gravel. And sometimes you would have more than one. Where you would have you'd have large gravel particles, and we have the small sand particles, and some really small sand particles, and then the clays. Something like that. And they would be done in this fashion. With these are how to use filter materials. Today we have geotextiles to do this work for us, and therefore we have those, and we can use those either by themselves in some applications, or in some applications we might want to have a combination of both. Have, say, gravel, then some kind of sand, then a geotextile, to really keep our filtration proper, to allow water to flow through and not the fine particles of the cohesive soil. But filtered materials are traditionally the way we've dealt with this. But I said, now with geotextiles, we have another weapon in our arsenal to solve this problem. And that's it for our lectures on permeability. Until next time, thanks for watching, and God bless.